Oh yeah, I'll figure out. Oh yeah, I will ask you next morning. Like, how are you? Look at the star. I know this first. So we'll do a few concepts. And I go, like, showed up. Able to see. Anyway, so we. Yes, my skin got us stuff. You watch it's over. You walk over. You walk like stranded and all the way. Yeah, it's like what about.
All right, guys, page 17 in your packet. This is the last set of notes before our quiz review. So Friday, we talked about this test called first derivative test. And it basically went on to show that if we're looking at the f prime, or if we're looking at f prime data, we can find out information about where the graph is rising, where the graph is falling, relative max, relative min. Okay. Today, we're talking about the test for concavity. It says concavity test, but I'm going to rephrase it, test for concavity. And this is basically going to tell us about the curvature of the graph. So we're just getting into a little bit more detail about our graph. We know that our function f of x graph will give us the physical location, the points on the graph. F prime is going to give us the slope of the graph. And then now we're going to look at within that graph, what's the curvature of the graph within the positive and negative slopes. So here are some examples. We have this graph from left to right. What do you notice about the slope for this graph here? Positive or negative slope? Positive. What about this graph? They're both positive, right? But you can obviously tell that they look a little bit different from each other. Oh, she's not here today.
A note too, right here. Thank you. Thanks.
So we can tell that the graphs look a little bit different from each other, right? They're both positive slopes, but the curvature feels different. So what I want to kind of talk about is that they're both positive slopes, but if we look at what's happening to the slope of the tangent as we move from left to right, we see that the steepness of my positive slope is increasing. Right? So this is going to tell us something about the curvature a little bit later. Here, this graph is also positive slope, but you can tell that the pattern is the slope of the tangent is getting more less and less steep and more gradual, right? So maybe a slope of 4, then 3, then 2, then 1/2. Okay. So both of these functions are increasing. Yes, that's true. What do you know about their derivatives? Okay. Their slope values they're changing in different ways. Okay, so let me talk then about the two categories here. We have graphs that are concave up. And then we have graphs that are concave down. So a concave up graph is one that resembles a parabola opening up. Okay? And the concave down graph is where the curvature feels like it's part of a parabola opening down. So here, the common pattern here is that the slope values, and we always read from left to right, the slope is becoming more positive. And then for concave down graph, your slope is becoming more negative. So I'm just wanted to estimate the slope values at each of these points. These are not by no means accurate, but they'll kind of give us an idea of the movement of these slope values. So here, if we start at the furthest left here, what would you consider the slope here to be? Positive or negative? Negative. Steep or gradual? This point here. Pretty steep, right? So maybe like -4, -5. I'm just picking up some random numbers here. And as we move towards the center, what's going to happen to these slope values? It's going to move towards what? 0, right? Eventually, it will hit 0, and then it starts to increase again towards positive 1, 2, 3, 4, right? And look at these numbers here. We consider these numbers slope becoming more positive because all these numbers are kind of headed towards a positive value, right? If these were numbers on number line, we'll be continually moving to the right, right? -5, -4, -3, -2, 1, 0. So as long as the slope is becoming more positive, then your graph is going to resemble this shape. It's going to resemble this concave up shape. All right. Meanwhile, over here, if I start at the end here, I'm having it start off with a positive slope, maybe 5, then 4, 3, 2, 1, 0, -1, -2, -3, -4. And you see all these numbers here. These are all ballpark slope values. All these numbers are moving in a negative direction. If these were numbers on a number line, we'll be continually moving left. And then if we had all these slope values, then the graph that's going to show up is going to one that resembles parabola opening down. I want to draw one more graph here. Let's say I had a graph that starts off concave down, then it goes to concave up. So it's going to do some ballpark values here. So this is 5, 4, 3, 2, 1, 0, -1, -2, -3. At some point, it's going to start moving in a negative back towards positive. So -3, -2, -1, 0, 1, 2, 3, 4. So you see here that there's a point when there is this change where the graph starts moving in the opposite, right? This is moving towards a negative number, but then it's going to eventually stop and move towards a positive number. And that change in concavity is what we call a point of inflection. It's that point where the steepness is going to start moving in the other direction. If it was moving towards a negative value, it's going to start moving towards a positive value. And a lot of times I abbreviate it using 3 letters there, POI, for points of inflection. So visually, this is not always the case, but sometimes the easy way to pick up point of inflection is imagine you're on a roller coaster ride and you're trying to identify where the steepest part of your graph is, or the steepest part of your ride. So steepest part of your ride is typically going to be where your points of inflection is going to be. That's where that steepness is going to start. Maximum steepness has achieved, and it's going to start rounding out towards the other direction. So our test for concavity, we're going to find intervals where our graph is concave down, where the graph is concave up, where there's a point of inflection. And the way we do this through calculus is we're going to get everything from the second derivative function. So remember the first derivative test, we set f prime equal to 0. We create our slope sine line. Now we're going to find our f double prime graph function, find the critical points from f double prime, and then create its sine line. So when we do that, we're essentially going to be, the process will feel the same as the first derivative test. It's just that everything we're gathering is at the second derivative function level. So we may find critical points, and then we're going to test points in each subinterval with the second derivative function. Let's say we get positive. Then to indicate that the graph is concave up, we're going to use a U shape to indicate how the graph is going to actually look. Just like how we use arrows to kind of help remind us how the graph is moving in terms of its slope. From the second derivative function, we can gather information about the curvature of the graph. And to help remind us that we're looking at the curvature, we're going to use either a parabola opening up or parabola opening down to help us visualize the shape. Okay. So here's example 1. We're going to find points of inflection and intervals of concave up, concave down. So this is the test for concavity, and we're going to gather everything from the second derivative level. So we have to make our way down to f double prime. We'll go through power rule twice. So f prime first. Power rule. Power rule here as well. Bring down the 3. The 3 and 1/3 cancels out. We want to keep going because if we were to stop here, then we would be gathering information about the slope rather than concavity. So moving on to f double prime. Power rule again. Now we can set this equal to 0. I can factor out my GCF of 10x. I'll set both equal to 0. If the square root, plus or minus shows up. So x equals plus or minus root 1/4, which I can clean up to be just basically plus or minus 1/2, right? Take the square root of 1/4, I get 1/2. Got 3 critical points, 0, 1/2, and negative 1/2. So let's create our f double prime sine line. So what we plotted here, these are now going to be our potential points of inflection. So points of inflection is where concavity changes, either from concave up to concave down, or from concave down to concave up. There has to be a change in signs in order for us to call these points of inflection. Just like with our first derivative sine line, we're going to pick points in each subinterval to test. So here to the left, I'll choose -1. Between -1/2 and 0, I'll choose -1/4. Between 0 and 1/2, I'll choose 1/4. And then to the right of 1/2, I'll choose 1. We're going to plug this into our f double prime because we're trying to gather information about concavity. So -1 and for x, -1, that's negative there. -4 plus 1 is negative, so 2 negatives makes positive. So my interval is positive here. I'm going to indicate with a visual connection that the graph is going to resemble concave up in this first interval. If we use our calculators to plug in -1/4, we'll get negative, and this will give me positive. So negative times positive is negative. Concave down. Plug 1/4 in. Positive times negative. Positive times positive will be positive. And if I plug 1 in, positive times negative is negative. Okay. Just like how we did with first derivative test, once we are done with our test points, we're going to cross them out. They're not going to play a role in any of our interval statements. The whole purpose is just to populate the top of the sign lines. After that, we're not going to use those numbers again. Okay, so here are the statements that we can write. We're going to write out our statements just like how we did with our first derivative test. We're going to gather information about concavity, where our intervals is concave down, and where the graph is experiencing points of inflection. So concave up, we have two subintervals here, from -∞ to -1/2, and also from 0 to 1/2. So we can say our function is concave up. Because f double prime is greater than 0. F of x is concave down. -1/2 to 0, and then from 1/2 to infinity. Because f double prime is less than 0. And finally, points of inflection. I'll abbreviate POI at okay, how do I get these y values? -0.146, the 0, and the 0.146. How will we find those numbers? These are points. So where do we find information about points? Original. Yeah. So if you want to find those y values, take the -1/2, the 0, and 1/2 individually, insert them into the original function, and then whatever you get back is the physical y value location at the points. Our justification here is not like relative max, relative min, where you have to say, oh, because my sign changes from positive to negative or from negative to positive. You can, but you could also just simply say because f double prime changes sign. That's good enough. We don't have a distinction in terms of the name for the points of inflection where the order matters. Okay. So as long as it changes signs, they're both considered points of inflections. So Friday, we talked about first derivative test. Today, we started off with something called the test for concavity. And now I have something to talk about, and that is called the second derivative test. And that feels kind of strange, that name, because it feels like this should be called the second derivative test because we're using the second derivative function to create sign lines and everything. But this is called the test for concavity. And there's something else that is what is called the second derivative test. Next page, page 18. So the second derivative test is a test for relative max and relative min, and it's not what we just did, points of inflection. And this feels a little bit strange because we already have a test for relative max, relative min, right? That's the first derivative test. But we have another test that does the same thing, also finds relative max, relative min, but it's using the second derivative function. Okay. So the second derivative test achieves the same result as the first derivative test. Basically, we're going to find the critical points the same way. We're going to find f prime, set f prime equal to 0, find those critical points. But rather than taking those critical points and plotting them onto our sine line, we're going to insert them into the second derivative function and look to see what it gives us. If it gives a positive number, it'll tell us information about relative max or relative min versus plugging in and getting a negative number. So just to demonstrate visually what's going on, let me draw a function graph. Let's say a graph looks like this. And let's say there was a critical point at 1. Right? What would you say f prime of 1 would be? Basically, what is the slope at 1? 0, okay. What about f double prime at 1? At this point, what is the concavity at this point? It's part of a what? Concave up. So therefore, f double prime of 1 will be greater than 0. It could be 3, it could be 6, it could be 12. It's basically any number that you see is going to feel a little abstract. Just understand that it has to be positive. So the idea is that if I can pair up this information, if I know a point is slope 0 and concave up, then without even looking at a sine line or a graph, I can conclude that there must be a what? Relative minimum at x equals 1, right? Meanwhile, let's say I had a graph that looked like this. What would f prime of -3 be? Zero, because the slope is 0, right? What would f double prime of -3 be? Less than 0, right? So concave down. If I pair concave down with slope 0, without even looking at any more information, I know it has to look like this. If it looks like this, there must be a relative max at x equals -3. So I want to show you the steps for second derivative test with example 2. But I think something that will make it a little bit easier, or so we can see the steps more clearly, is we'll do this both ways. We'll do this using first derivative test, and we'll use it, find the relative max, relative min using second derivative test. So you can kind of see, how they're similar, but then also where they begin to have different steps. Okay, let's do the easier one here first. So we'll find relative max, relative min using first derivative test. So f prime 3x squared minus 8x minus 3. Set f prime equal to 0. Go through our factoring. Solve for x. We plot our f prime sign line. We test each subinterval. Okay. Into our f prime. We get a negative times negative, which is positive. Plug 0 in. Positive times negative is negative. Plug 4 in. Positive times positive is positive. What can we conclude here? What do you expect at negative 1/3? Based off the arrows. Relative what? Maximum. Yeah, the graph is rising followed by falling. So we know that there's a relative max at x equals negative 1/3. What do you expect at 3? Relative min, right? The arrows are kind of indicating how the graph is moving. The graph is falling, followed by rising. So relative min at x equals 3. Okay. So we know this is true. Let me show you what the second derivative test looks like. Well, we'll get the same results. Same result, but a different path. Let me show you from beginning to end so we can kind of see all the first steps will be the exact same. Okay. You're finding f prime, you're finding critical points. Right, same candidates, right? But rather than going through our slope sign line, we're going to do something else. We're going to find f double prime. Okay. That's why it's called the second derivative test. This is where f double prime plays a role in this process. So what's f double prime going to be? Okay. Let me tell you what we're not going to do. We're not going to set this equal to 0 and solve for x, because then we're doing something else. Then that's test for concavity. Okay. So we're not going to find critical points here. What we are going to do is we're going to take the candidates that we found from f prime, and one at a time, we're going to insert them into f double prime. Okay. So, but we'll get the same result. F double prime of negative 1/3. So 6 times negative 1/3. Okay, what does that give us? Negative 10. Now this number is a little bit abstract, but what we really care about is the fact that it's what? That is negative. That's all we care about. That is negative. And if I know that negative 1/3 has a slope 0, because I found that from f prime, if it's slope 0 and a negative second derivative value, what does that mean? That must mean that at this point, the graph is what? Concave. Down. Okay, so concave down. And if we visualize that graph, right, concave down looks like this, and you're pairing slope 0. So if it's concave down and slope 0, this point must be a what? Relative max. Yeah, so we can say relative max at x equals negative 1/3.
I had a question on I was confused with how the f double prime graphic comes down to the x-axis at x equals 3. Because there's I'm confused about the relationship between this and this.
Because at this point, there's a change in concavity, so that must be a
function.
Because I'm looking for slope 0. Any slope
Right.
0 or slope undefined is going to have to sit on the f
Okay.
prime.
Okay. So it doesn't matter if it's a point of inflection per se, but even if it's like slope 0 or slope undefined, it has to come down.
Yeah, it's come down, that makes sense.
So here, I don't have to get it through my head that like only points of inflection are on the x-axis, but rather it's not just point of inflection, but it's anywhere where slope becomes undefined or 0. Is that where you're?
That's right.
Okay.
That's right, yeah.
Okay, thank you. That clarifies that a lot.
Okay.
Okay, f double prime of 3, right? And this is consistent with what we found before, right? Relative max at -1/3, relative max at -1/3. F double prime at 3. We're plugging 3 into f double prime. 6 times 3 minus 8, what does that give us? 10. The number is not that important. It's the fact that it's what? It's positive. Therefore, this is part of concave what? Concave up. If the graph has a concave up shape and it's paired up with slope 0, this must be a what? Relative minimum. So relative minimum at x equals 3. And that's consistent with what we found with our slope sine line, right? Relative minimum at x equals 3. So let me take this information and ask a question just from this perspective. Okay? And let me show you where the trouble spots that students experience. But let me just give you another moment here. So let's say I phrase this question a little differently with limited information. Let's say I told you that f of -1/3 was at 4. That's just going to be some order pair, right? And then let's say I told you that f prime of -1/3 was 0. And then f double prime of -1/3 is equal to -10, just like what we did before. Would you be able to tell just from this information alone that there is a relative maximum at -1/3? Right. Let's just go from this perspective here. So we know there's an order pair of -1/3, 4. So whatever that point looks like. We know that there's a slope 0 at -1/3. We don't know what that looks like yet. We should know slope 0 can be relative max, could be relative min, could be neither. But this is going to help us pin that down, right? -10, that means this graph is concave down. If it's concave down, the graph looks like this. Therefore, there's a relative max at x equals -1/3. Right. We're doing the exact same thing here. I'm just giving you information where there's no way for you to do first derivative test because you only have limited data and you're forced into second derivative test knowledge. But here's the trouble spot is why do you think a lot of students, when they see this, they would say a relative minimum and not a relative max? Because this is where the trouble spot is. Because it's negative. And they think negative is a location that's below the x-axis, and that must mean maybe a small value relative minimum. But remember, this is not a y value. This is an abstract concavity value, which we don't have to, it's going to be, no, we're not going to be able to differentiate what does a concavity of -5 look like compared to concavity of -6. What we can distinguish is the fact that it's negative. And that negative is going to translate to concave down, which must mean a relative max. Okay, so just want to point out that trouble spot. Likewise, when students see a positive number from second derivative, they think, oh, that's a big number. That must be a relative maximum. But it's opposite because this is not a location value. This is a curvature value. Concave up looks like this. If it's concave up, you know that you're looking at a relative minimum. Okay, so we're moving to our quiz review packet. Okay, it says find critical numbers. So critical numbers is just where slope is 0 or slope is undefined. Now, there's not going to be any slope undefined here, so we just set f prime equal to 0, find our x values. But if there was a denominator with f prime, we would also set the denominator of f prime equal to 0. The 2 is not going to produce any critical points for us, so just 3x minus 5 and x minus 1, I get 5/3 and 1. Okay, find absolute extrema. What theorem are we applying here? Extreme value theorem, right? Now, on the quiz, on the test, I'm going to ask you if it's extreme value theorem, mean value theorem, or Rolle's theorem, you need to be able to write the conditions. What condition is required for extreme value theorem? Function needs to be what? Continuous on the closed interval. This is a polynomial, so that's easy one to decide. No issues with continuity, but we have to make sure we write out that statement. Okay? I'm looking for that statement to earn full credit. So extreme value theorem, we're trying to find the highest and lowest points on the graph. That means we want to look for candidates. So candidates, we're always going to make sure that we test what? Endpoints are candidates. And then we also need to find, besides endpoints, we also want to find what? Critical points. Yeah. So we're going to set f prime equal to 0, find those critical points, and make sure that we have valid critical points. That means they have to land inside the interval. And we got to test endpoints and critical points. So trouble spot that I see students experience with EVT is they would test the critical points, but they would forget about the endpoints. So make sure that you also include endpoints as proper candidates. And then when you find your candidates and your endpoints, you're going to plug them all back into the what? Now we're looking for locations, so they all get inserted back into the original function. And then we look at the y values, right? Highest y value is your absolute max. Lowest y value is your absolute min. Use your calculators for that. Both 2 and -1 are valid critical points because 2 is clearly between -2 and 3. -1 is also between -2 and 3. Okay, any questions with 2? All right, number 3, we want to determine if Rolle's theorem applies. So Rolle's theorem is like mean value theorem. They're basically the same thing. What conditions are required for Rolle's theorem and mean value theorem? So continuous and what? So continuous with brackets and then what with parentheses? Differentiable, yeah. So continuous just means that it's no asymptotes, no holes. Differentiable, I won't give you any problems. That's continuous, but not differentiable. So if you can make it past the continuity condition, it will also pass the differentiable condition, at least for the ones that I gave you for now. So just have to check for continuity. That's really the only thing that we have to worry about. How do we check for continuity? Look in the where? Denominator, right? Because denominator is where the holes, asymptotes can occur. So there is, what's happening? What can you tell? What does the denominator tell us? There's a what? Vertical asymptote at 0. Is that going to interfere with our interval? Yes. So if there's a break in the interval, it affects our problem. We can't move forward because we can't get that condition to pass. So our function is not continuous. Therefore, Rolle's theorem doesn't apply. Right? Our continuity condition from -2 to 2 is not met. Number 4 is mean value theorem, but it's a little bit more complicated than what you'll need to be able to do. So let's skip number 4 and let's see if we can just try number 5. Number 5 is first derivative test. Find intervals where our function is increasing and decreasing. So find f prime, set f prime equal to 0, plot your sign line, and then write out your because statements. When you test your numbers on your slope sign line, they're going to be testing against f prime, right? Your factored form of f prime. I just chose a decimal number between 1 and 5/3. I chose 4/3. But either way, we plug them into our derivative function. Positive would mean my graph is rising. Negative would mean my graph is falling. There's clearly a relative max at 1, relative min at 5/3, but this problem is only asking for increase, decrease. And then we have to write our because statements. Any questions? All right, let me talk about the updated calendar here. For homework tonight, that's due on Wednesday. We're basically just going to finish off the rest of the problems that we didn't do for 5.3 from Friday, but we're going to still cross off 94, 99, and AP practice 1 through 4. You're just doing the 47 through 92, the rest of the problems here. Tomorrow, no school, PSAT day. Wednesday, we'll do quiz review. I want to give you a little bit more breathing room here, so I'm going to swap Thursday and Friday. Quiz is on Friday. We're going to cover 5.4, which is curve sketching, not on the quiz, but it is review. We can also spend some time reviewing on Thursday. So quiz is on Friday. All right, can get your phones. Yeah. So, do you have time to do quiz review these next few days? So I would, go through worksheet 2. Worksheet 3. So do as much of that you can, and then let me know tomorrow if you have any questions. I can also answer some questions for you Thursday. I'll have a session Thursday morning. And it's yeah, so if you feel comfortable with it.
I need, like, for the normal school day, I need the first thing. So
Yeah.
like, I'll make a session.
Yeah, think about the health session.
Like the first period?
Yeah.
Okay, and then for the class.
Oh, right, for, yeah, for class, you can just watch it over the weekend.
Okay, I got you.
Thanks.
I really like to different perspective.
That's so pretty. So. I love the joke. I used to.